the aim of this work is to try and model the crack propagation in silicon anode for lithium-ion battery, and in particular in silicon thin film with a thickness of about several hundred of nanometers. Okay, so the motivation of this work is that the capacity loss in silicon-based battery has been shown to be related to the early failure of the anode material. Like in this SEM picture, you can see that the thin film really intensive failure crack network has been developed in the thin film, and also you have decohesion here between the thin film and the substrate. And so this failure network caused the capacity loss of the battery. So there is a big issue in understanding this failure mechanism in order to be able to improve the performance of battery system. Okay, so we want to build a model that will be able to account for the ion diffusion within the thin film, to take into account also the influence of ion insertion on the insertion in the material, and to reproduce experimental crack patterns. And so we would like to be able to model the delamination between the substrate and the thin film, and to investigate the influence of patterning the thin film. We try to build a model that will be as simple as possible. So the idea is that, of course, it has to be multi-physics, and we start with the mechanics part of the model, which is just the balance of mechanical momentum written in its more simplest expression. So sigma is the Cauchy stress tensor, and we assume that there is no body force. We assume that we are in a small strain framework, and processes are quasi-static. So you can't do something more simple than this. Ion diffusion is modeled with a fixed law, which says that the change of concentration of ion is related to the Laplacian of concentration through a diffusivity coefficient. So C is the normalized ion concentration, meaning that when C equals 0, there is no ion in the material, and when C equals 1, the material is fully inserted. And of course you have to couple these two physics, and this is achieved through this equation, which states that when ions are inserted in silicon, then it produces a volume change in the solid material. And so this volume change is modeled through this chemical induced strain, which is proportional to the ion concentration C through dilatation coefficient alpha. And then we split the strain into this chemically induced strain and the elastic strain. And we state that the total strain is the sum of these two contributions. Also, we adopt a nonlinear diffusion coefficient that will make the concentration profile really sharp, that will induce a strong stress, large stresses in the seal film. Okay, so at this point there is no failure in the model, so we choose a phase field gradient damage model to model failure. The idea of this model is to replace a sharp crack description by a diffuse crack concentration D. For D equals 0, the material has no damage. For D equals 1, you have a crack. Okay. So I will not go into the details of the thermodynamics framework that is behind this model because I have no time for that. However, you have an equation that governs the damage evolution for this model. And in this equation, so you have D here, and you have two parameters, GC and LC, which are the fracture energy and an internal length scale that govern how diffuse is the damage evolution around the crack. And in this formulation, you have an history function here that allows you to ensure that the process of damage is irreversible. And in the model we built, we assume that phi is the maximum during time of psi plus, which is related to the strain energy density. And we will assume that the shear part of the strain energy density always increase damage, but concerning the spherical part of the strain energy density, so the one which is related to the volume change, only positive volume change will induce damage. Meaning that when you have contraction of the material, you don't induce damage. This will also allow us to somehow account for unilateral contact. And when you derive all this equation, you at one point you end up with an expression of the effective stress that is related to the local damage and also the local strain. And you retrieve the fact that we have always damage for the shear part, whereas for the spherical part of the strain, we have only damage for positive volume change. Okay, so let me now show which kind of result you can obtain. So this is a first example on a thin film failure. So these are SEM picture of the thin film after lithiation, meaning that we have lithium ion have been inserted into the thin film. So the thickness of the thin film goes from 500 nanometer to about 1000, meaning that you have double the thickness. And because the thin film is strongly attached to the substrate, this constrains the expansion of the material. And because you constrain the expansion, you are, it leads to tensile stresses inside the thin film, which lead to failure. So this is the basic mechanism of failure initiation in this case. So this result we have been able to reproduce. So you have some of the parameters we use. So we are analyzing a square domain of 10 by 10 micron with this material parameter. So you can see here in color the out-of-plane displacement of the thin film, and you can see that it is about 500 nanometers for an initial thickness of 500 nanometers, meaning that we reach the final thickness of the fully inserted thin film of about 1000 nanometers. So this means that we have the good dilatation coefficient. And you can see also that we have the initiation of a crack network during this first lithiation. Okay, so this is a good point, and after that we have some experimental results after the first delithiation. So during delithiation, lithium ion goes out of the thin film, and you have further cracking of the thin film. And also what you can see in the SEM picture is that you have delamination here between the thin film and the substrate. And you can see that the island here that you have in the substrate somehow bends due to this delamination. And this also we have been able to model. You can see here in pink, this is the crack surfaces, and you can see that we have some island exactly that as in this picture, and also that we have delamination between the substrate and the thin film. And also, if you look at the out-of-plane displacement, you can see that the island somehow bends also exactly that, as in the experimental picture. Okay, so to try and avoid this early failure of the thin film, my colleague has the idea to etch some nanopores in the thin film. So it has the effect that it is easier for the material to accommodate the expansion of the material due to ion insertion. And this is what you see in this picture. So you have some kind of curvature here of the material between two holes, and here the wall of the material is somehow inclined due to this expansion. And thanks to these nanopores, you have no failure during the first insertion. Whereas for the thin film, we had failure for the first lithiation. Okay, and so the model also is able to reproduce this result. You can see here what we have after the first lithiation. You recognize well the shape here of the material between two pores, with some curvature here and some inclination of the wall here. And after the first dilithiation, where we have the formation of the crack network that goes along the diagonal between the holes that have been etched in the seal film, and we have also some kind of delamination around the hole. Okay, and so this result we also get quite well. You can see here the crack pattern that we get after the first dilithiation, and we recognize quite well the diagonal crack patterns. And you can see also in this picture that we have delamination starting from the hole boundary and going inside the material. Okay, so I now come to my conclusion. The model that we built has several limitations. Of course, there is a weak coupling between chemistry and mechanics. We are working with small strain, whereas the material is experiencing extremely large strain. And we have no influence of lithium insertion on the elastic behavior of the alloys that form during insertion. However, the model shows the ability to take into account the influence of ion insertion and de-insertion, and to reproduce experimental crack patterns and delamination as we would like to do at the beginning of the story. Thank you for your attention.
Thank you.